Hey everybody, I'm going to make a video for us, so I guess this is going to be for Monday, October 19th. I am recording this on the 18th. I'm moving today, so I hope you enjoy this video while I'm busting my back, moving heavy boxes into my new home. Anyways, what we're going to talk about today is something called the sum and quotient rules. Oops, I just realized that I already have a typo. It's not the sum and quotient rules, it's the product. It's the product and quotient rules. I don't know why I wrote sum product. There we go. Hopefully that's the only typo that I've written so far. I kind of wrote a little bit ahead, and now I'm going to record a video. I kind of want to make this a short and sweet video, even though there's a lot we have to talk about. So, product and quotient rules, what's that all about? Well, let's say we wanted to calculate this derivative, the derivative of x times e to the power of x, okay? So that would be the product of two functions whose derivative we know about already. We know the derivative of x, and we know the derivative of e to the power of x. But do we know the derivative of x times e to the power of x? That's the question that we've been asked. So yeah, we know d by dx of x, that's equal to 1, right? The derivative of the function x is just equal to 1, because the slope is always 1. And we learned this, I think it was on Thursday, that the derivative of e to the power of x is e to the power of x. I'm hoping that that's your favorite function these days. It's a really great function, a lot to be said about e to the power of x. Most notably that the derivative of e to the power of x is itself. Pretty cool. So what about their product? Okay, well, we've seen before that the derivative of a product of functions is not equal to the product of their derivative. I think I pointed that out a few days ago. I forget exactly which day, but it certainly is the fact that these are not equal. And if you don't believe me, try calculating the derivative of x squared, and then try to factor x squared into x times x. And you'll find that the derivative of x squared is not the same thing as the derivative of x times the derivative of x, right? I think that we've seen this is 2x, and this over here is 1, and that would be 1. 2x is not equal to 1 times 1, right? So I hope that's obvious. We can't just multiply their derivatives together. That's not how it works. So we need to see what happens with the derivative of a product of two functions, and that's what the product rule is telling us about. So that brings us to a theorem. Yay! Okay, let's talk about the theorem that is often referred to as the product rule. So the product rule tells us that if f and g are differentiable functions, then the derivative of f of x times g of x, so the derivative of the product of two functions, is equal to, well, the derivative of the first function times the second function plus the derivative of the second function times the first function. So there's a lot of symmetry here. It's really nice that way. Another nice way of putting it that just uses less symbols is that fg prime of x is equal to f prime of x times g of x plus f of x times g prime of x. I've even seen it written in using less symbols. I've also seen this. I've seen fg prime is equal to f prime g plus g prime f. That's like super shorthand. So if you want, you could write that. That's the kind of thing that you would save for maybe like a cheat sheet or something like that, or a formula sheet. Sorry if you can hear a bunch of crashing around. Those are my cats. Pardon me. Okay, let's talk about the proof of this. So where does this come from? Why do we get this? So there's a lot of proofs out there. There's some geometric proofs, and I thought about maybe showing you one of the geometric proofs. But the thing about the geometric proofs is that they do take a little while to sort of understand. I think that I would encourage you to look at some of the geometric proofs out there. I think that Wikipedia has a geometric proof. Our textbook, the Stewart book, has a geometric proof. So if you want, you can look for a geometric proof. I'm going to show you an algebraic proof, okay? And the reason I want to show you an algebraic proof is because I want you to appreciate kind of some of the ingenuity that went into some of these theorems. It's not obvious how to do this question. Okay, just hold on one second. Goose, psst. It's enough. Pardon me. Okay, let's talk about the proof. Okay, so remember that. So let's say that h of x. Actually, let's call it k of x. Let's call it k of x. Let's say that k of x is equal to f of x times g of x. Okay. And we'll also say that d by dx of k of x, well, that is equal to the limit as h approaches 0 of k of x plus h rather, k of x plus h minus k of x all over h. You can see why I didn't use h of x, because it would get a little bit confusing with all the h's. So no h of x, because we're using the variable h, and that might get confusing. So we're using k of x. Okay, so I just did this because well here's what k of x is. So now we can just plug our original functions back in. So no worries. I know that this is going to be equal to the limit as h approaches 0, and k of x is f of x times g of x. So k of x plus h is going to be f of x plus h times g of x plus h minus, and then k of x, that's just f of x times g of x. And that's all divided by h. Okay, so we could stare at this for some time and think about things we could factor out and that kind of thing. I think that if we did that, we'd be stuck. We'd be stuck for a little while. If you look at this and you ask yourself, well, boy, what do I do now? I don't see any sort of relationship to this and whatever that formula is, this one here. Well, that's okay. You're not really expected to. You're not a mathematician, not yet anyways. And you haven't thought about this for very long. And that's why I wanted to show you this proof, because I'd like you to appreciate some of the ingenuity that goes into these theorems. From what I understand, I believe it was Leibniz. So Leibniz is one of the founding fathers of calculus, along with Isaac Newton and several others. And Leibniz thought, well, what if I add something to the numerator and then subtract it? Sometimes you might multiply something by 1 to simplify it, but it's not actually 1. It's like the square root of 2 divided by the square root of 2, simplify it. So Leibniz had that idea. So Leibniz decided that he was going to add and subtract just the same thing. So I'll show you what he did. And this is where our proof is going to start getting a little more hairy. So what I'm going to do is I'm going to just start writing my limit all the way to the left over here to give me a little bit of extra room. So this is limit as h approaches 0 of, I've got f of x plus h times g. I'm going to even squeeze that in. G of x plus h. Okay, and I'm going to just make a nice big bar like that. I think I might need even a little more space, but that's okay. You know what, I'm going to leave the bar out for now, and then we'll just fill it in when we're done. And then the thing that he decided to add and subtract was this beast here. So he decided to subtract f of x plus h times g of x. Okay, so he subtracted it, and then he added it, f of x plus h times g of x. Ta-da! Okay, doesn't look like much yet, but we'll see that this is going to turn into something. And then this, and then don't forget to do the minus f of x times g of x at the end. Okay, and we have a big old h at the bottom. What can we do now? What can we do now? Okay, well, let's see what we have here. Let's see what we have. Okay, so I'm going to, I'm going to split this up. I'm going to split this up into two different things. On the left here, I'm gonna have the limit as h goes to 0 of, well, I'm gonna take those first two things. So I'm gonna have f of x plus h times g of x plus h minus f of x plus h times g of x all over h. And using the limit laws, we can split up this sum into two different limits. So the limit as h approaches 0 of, well, this portion. So I've got f of x plus h times, f of x plus h, there we go, g of x minus f of x times g of x. Ta-da! And that's all over h. Beautiful. Look at that. Okay. Now, what can we do with this? Well, let's see here. Now that I've split it up, I've got a few things that I can do. I can start factoring some things out. See, this was a really smart thing to add and subtract, this little thing over here, because it lets us factor this out on that side and lets us factor this out on that side. Okay, so over here on this portion, what we're going to do is we are going to factor out this, and then on this portion, what we're going to do is we're going to factor out that. Okay, so what I'll do is I'm going to color code it just so we can kind of see what's happening here. So let me change that to, let's say, green, and then I will change, I'll change this to green too. So green will be the thing that we're factoring out. So we're going to factor out those green guys. So on the left here, let me choose the color green. So over here, this is going to be the limit as h approaches 0 of, what am I doing? I chose the wrong thing to factor out, or I chose the wrong thing to color. Pardon me. Okay, so this should actually be pink, and it's the f of x plus h. That's what we're factoring. Excuse me. You can tell that I'm doing this in one take. And, oh, come on. Change that color back to pink. There we go. Okay, beautiful. All right, so yeah, let's factor out that f of x plus h, f of x plus h, and what I'm left with here, is g of x plus h times, minus g of x all over h. Okay, I factored out that f of x plus h. And on this side, I get the limit as h approaches 0 of, okay, and I'm going to factor out that g of x. I'm going to factor out that g of x, and I get f of x plus h minus f of x all over h. Okay. So we are going to apply some more of our limit laws, okay? So applying some of our limit laws, what we'll see is that, well, the nice thing about a limit is that if our functions are continuous, then we can really kind of be liberal with how we treat our limits. And the nice thing about this is that we know that our functions are continuous because they are differentiable, and differentiable functions are continuous functions. So what that means is we can actually start putting this limit pretty much wherever we want. Well, not really wherever we want, but we can be quite liberal with it. So the idea is, okay, well, this is a product of two limits, which means that I can turn that into the product of two limits. So this limit will go into here, and the limit as h approaches 0 of f of x plus h, that's just going to be f of x, okay? Because h is going to 0, and there's nothing wrong with that. It's not going over to 0. We're not subtracting it by anything. Like this thing right here, this is just f of x, okay? But now we're taking the limit as h approaches 0 of this as well, right? So the idea is that we're taking the limit of a product, okay, which is the product of limits. So this is one of the products, and there's really nothing wrong with the limit over here. So this is just f of x, okay? So this is, and I've been missing my equal signs here, so this should be equal. So this over here is f of x, and when I take the limit of this thing over here, when I take the limit of this, well, that's just the derivative of g of x by definition, right? So when I take the limit as h approaches 0 of this thing, that's just g prime of x. So this is g prime of x. All right, look at that. And over here, well, nothing's happening over here. There's no h. So again, we have the limit of a product, which is just going to be the product of the limits, because these are all continuous functions. So there's no h over here, so no problem. So this is equal to plus, well, I've got my g of x over here, so here's g of x, and then this is the derivative of f, right? As the limit as h approaches 0 is f, and I should put that in pink rather, excuse me, f prime of x. And we're done. And it's often customary to put a little square at the end of a proof to indicate that our work here is done. So just like that, we've proved the product law. So I'm hoping that you can see just how ingenious it is to add and subtract that thing. Like I bet you that if we were asked to prove this theorem, it would take us a very long time to figure that out, right? Like that's a really nice thing just to add and subtract, okay? There are other proofs. The geometric proofs are really nice. I recommend that you take a look at that if you're struggling to understand where this comes from. But yeah, so there is our product law. So let's go through and finish off that question that we were asking. So d by dx of x times e to the power of x, well, that is going to be, well, the derivative of the first one times the second one. So the derivative of the first one is 1, and then I multiply that by the second one, so times e to the power of x. Then I add, well, I leave the first one alone, and I take the derivative of the second one. So, well, the derivative of e to the x happens to also be e to the x. So this is equal to e to the x plus x times e to the x, or if you like, e to the x times 1 plus x. Isn't that something? So there's our product rule. Okay, I'm gonna quickly show you the quotient rule. Be good for our purposes. So the quotient rule looks something like this. Okay, so the quotient rule says that if I take let's say that f of x is equal to g of x divided by h of x. Okay, so if I want to take the derivative of the quotient of two functions, so one function divided by another, well, there's a rule for that. We say that f prime of x, so the derivative of this quotient of functions is equal to g prime of x times h of x. So the derivative of the first one times the second function, kind of looking familiar a little bit. This time we take a subtraction. We do minus g of x times h prime of x all over h of x squared. H of x squared, what the heck? So we're going to leave the proof for this one. I mean, we don't really need proofs in this class. This is not a theoretical calculus class. This is very much an applied calculus class. We don't actually really need to prove this, but I think that it is useful to see the proofs just to get a sense of where these things are coming from. So we'll do just a quick example, and then I'll end the video there. So let's try calculating d by dx of, let's do e to the x over x cubed. Okay. So this is going to be, well, if I take the derivative of the quotient of two functions, what I do is I take the first function, the numerator, and I'll take the derivative of that. Well, the derivative of e to the x is e to the x. And then I leave the second function alone, so that's x cubed. Then I will subtract. Well, here I leave the first function alone, so I leave the numerator alone, e to the x, and I take the derivative of the bottom function, or the denominator. So that's going to be 3x squared. Okay, and that will all be divided by the denominator squared. So that's going to be x cubed all squared. And with these types of questions, we really do want to simplify it. So this is going to be, well, let's just kind of get rid of some of these brackets. So that's going to be e to the x times x cubed minus, let's say, 3 times e to the x times x squared all over, well, that'll be x to the power of 6. Okay, I think there's a few things we can factor out here. So I think we can factor out from the numerator an e to the x times x squared. And what I'm left with is x minus 3 all over x to the 6. And let's see here, that would be e to the x times x minus 3 all over x to the 4. So there it is. That's all there is to it. So we have the product rule and the quotient rule. So in our Stewart book, I'm just going to pull that up right here. Oh yeah. Oh, so here you can see the product rule, the geometric the geometric idea. So here's one version of it. There's other geometric proofs as well. I recommend that you check some of those out. Yeah, okay, so right over here, here's a nice little table of differentiation formulas. Let me just take a little screenshot of this, and we'll add this to our little notebook here. Let me take a screenshot. There it is. I will hit copy. Okay, and I'll go back in here and paste it. Here we go. Ta-da! So this is our little table of differentiation rules. This is very much worth memorizing. So we've kind of been adding to this bit by bit, and I added something of our own here. So this one right here, that's our the derivative of an exponential function. We don't typically take the derivative of the exponential function too much. But there it is right there. Yeah, so that's really all we're doing today. So for homework, what I'd like you to do is the following problems. So I'd like us to work on, okay, we'll do 1, 2, and let's do, oh my gosh, my cats are just going crazy. I don't know if you can hear that. let's do. I don't want to wear you out, but it is important that we practice these things. So let's do all the odd problems from questions 3 to 26. So we'll do all these odd problems. And then maybe at some point tomorrow, I guess, well you're tomorrow, and for me, because I'm writing this on Sunday, the day after tomorrow. But on Tuesday's class, maybe we can go over some of these more interesting problems. I really like these problems. They're very fun problems. I know that often kind of questions at the end, near the end of a section, are usually kind of ignored, but this is where all the cool stuff comes up. So I think that we should try some of these. But in order to really understand these problems and how to do them, it's important that we have the mechanics down, because we have to know how to actually apply these rules. Once we can apply these rules and we kind of see some of the subtleties of the rules from experience, then we can kind of go through some of these more interesting problems and see where they take us. So I'm going to end the video there. Hopefully you're having a good day. I miss you guys. I'm only going to be at school twice this week, so I don't really get to see too much of you. But anyways, if you have any questions, don't hesitate to ask. Like, I won't be at school, but I will be available. So yeah, take care. Goodbye. Take care of each other. And I will see you on Tuesday. Bye bye.